which will be circular motion. So also, if you have any doubts from HC Verma or the module, then you can please send them across in text message to me right now, and we will discuss those questions from your doubts also. Okay. So let's begin.
So sir, today will be start a new chapter.
So once again, I'm repeating, if you have any doubts in kinematics from HC Verma questions or from your module exercises, please send the question number to me on the text message, and we will discuss that in today's lecture also. Okay.
Sir,
Yes.
sir, so today is the last doubt lecture, and from next lecture we'll start circular motion.
Actually, we have completed the doubts in the last lecture.
No, sir, we did.
So on Monday we had a doubts lecture.
Yeah, that's what I'm saying. So are your doubts completed from HC Verma or anything is pending?
Completed.
Then we will
sir.
start with circular motion today. Okay. In case any doubts are pending, 1 or 2 questions or whatever, we can complete those also. Plus, I want to discuss a couple of more examples of relative motion. Okay. And then we will start with circular motion after that. Okay. So one of the type of examples I want to discuss in relative motion is going back to the situation of a swimmer swimming across a flowing river. Okay, in this we need to discuss 2 special cases. So the cases we want to discuss here are the shortest time to cross the river and the shortest path length to cross the river. Okay. So we have indirectly discussed both of these. Yeah, the recording is on, beta. Okay. Thanks for reminding, but the recording is on. Okay. So we have indirectly discussed this, but we'll discuss a little bit in detail about this situation. No problem, sir. So this being the standard situation, if this is a river of a given width with the water flowing at a certain given velocity along straight lines, certain uniform velocity the water is flowing at along straight lines. Okay, so if the width of the river is given to us, suppose that is d, and the flow velocity of the water, that is vw, okay, and the speed of the swimmer with respect to the water is equal to v. So then we know that the net velocity of the swimmer becomes the vector sum and all that. So now what we do is we take a general case where, let's say, the swimmer is himself swimming with respect to the water in this direction. So why I'm saying we take a general case is we'll take a general value of theta here. So this is the velocity of the swimmer with respect to the water, and this one has a magnitude of, let's say, v naught. Okay, so this vector has a magnitude of v naught. So then to find the net velocity, we have to add the velocity of the water, which is this vector here. So this is the velocity of the water. Okay. And the vector sum of these two. Now let's say in the general case, the vector sum of these two is something like this. So it is something like this, then the swimmer will end up with a net velocity which will be like this going in this path. Yes, very good. For the shortest time, theta has to be 0 per, that's correct. Okay, that's correct. Okay, so let's understand the logic of that also, why that happens. Okay, so in general, if the width of the river is d, so let us take our coordinate frame such that the origin is at the starting point and the y-axis is the axis which is perpendicular to the flow of the river, and the x-axis is the axis which is along the flow of the river. So in this case, we can see that the net velocity of the swimmer with respect to ground is the vector sum of the relative velocity plus the velocity of the water. So when we write this in component form, this will become what? The velocity of the swimmer with respect to the water, you can see its magnitude is v naught and it's at theta like this, you know, with the y-axis on the negative side. So the x component is minus sine theta and the y component is plus cos theta j cap, whereas the velocity of the water is v naught I cap. So the net velocity of the swimmer has an x component which becomes vw minus v naught sine theta I cap plus v naught cos theta j cap. Okay, so we can say that the net velocity of the swimmer in the ground frame in general has got both an x and a y component. You can always adjust the situation such that the x component is 0. Okay, but in general it is like this for this diagram, such that the x component, as you can see, is given by this, okay, and the y component is given by not cos theta like this. Okay. So now what will happen is, if he started his motion from here at t equal to 0, swimming like this, okay, then in general he will always be at some time it will be like this, and let's say he reaches here at time capital T. So by the time he reaches here, let's say he has drifted a certain distance s along the x-axis, okay, and of course he's crossed the river, so his displacement along the y-axis is d. So now, using the fact that he is ultimately moving at a uniform velocity, so his total displacement should be his net velocity into time. So using that equation only, we learn how to manipulate this for the two situations which I've asked about. One is the shortest time taken to cross the river, and for that, as you correctly said, Per, we'll see the condition that we'll get for the shortest time taken will be that theta should be 0. That means he should swim relative to the water in the direction which is perpendicular to the water flow, or in this case along the y-axis. Whereas for the shortest path length, we will get a different condition. So I'll come to that also. Okay, so if everything in this diagram and this place is clear, now we can see the next thing. So this is his net velocity, that is with respect to ground frame. Yes. So the net velocity, so now if he swims across in time t equal to 0 to t equal to capital T, suppose, okay, then it implies that the net displacement is going to be his net velocity multiplied by time, where s is going to be the net displacement. So referring to the above diagram, you can see that the net displacement is some distance he has drifted along the x-axis plus the width of the river along the y-axis. So we can even call this sx because it's the component of displacement along the x-axis. So that is this distance by which he is drifted down the x-axis. So this should be equal to the above velocity, which is Vx I cap plus Vy j cap multiplied by time. So now this equation, when we look at it, we can see that it has two implications. X component on the left hand side should be equal to X component on the right hand side. That is Vx t I cap. If we take the time inside the bracket. So we have the relation that displacement X component should be velocities X component into time. And similarly, displacements Y component, which is D, should be velocities Y component multiplied by T. So we have these two equations. So from this, you can see the second equation is going to give us the equation for time. So from equation 2, you can see that the time taken is d divided by Vy, which is d divided by Vo cos theta. So now you can see in this that for a given swimming speed, so Vo, that's a fixed quantity, and a river of a certain width, of the river, the minimum possible time to cross the river, that T minimum will correspond to d by V naught into cos theta's maximum, right? T will be minimum when the quantity in the denominator is maximum. Okay, so cos theta's maximum, as you know, is unity for theta equal to 0. This is the important thing. So you can see that the minimum time taken to cross the river is d by V naught. And the condition for this that theta should be 0. That means the person should swim. The velocity of the swimmer with respect to the water should be perpendicular to the flow. Okay. So that is a condition. Okay. So what we understand here, to cross the river in the shortest time or minimum time, okay, the swimmer must swim perpendicular to the flow of the river. So this is a factual thing now that we should remember for those type of conceptual objective questions. Okay, this is, so I'm just minimizing this and taking you through this once again.
Sir, can you scroll a bit?
Okay, so I'm just scrolling down to the next section. So you remember this result now. So whatever the width of the river, and more importantly, whatever the flow velocity of the river, it does not depend on that. It only depends on the width and the swimmer's velocity. And it's independent of how much the flow velocity is.
So the T minimum is.
Sorry, come again.
Sorry, sir.
Any doubt behind this?
No, sir.
Okay, okay. So as you can see also in this minimum time taken, this T minimum equal to D divided by V naught. This is independent. That means it does not depend on the water's flow velocity. It only depends on these two things, the width of the river and the swimmer's swimming speed. Okay, so now let's come to the situation of the minimum path length. Okay, the minimum distance. So the second case, minimum path length. Okay, so the path length is basically magnitude of s. So that is square root of this. Okay. So in this, there are two sub cases actually. Okay, one is where the horizontal drift can altogether be avoided. But for that, there needs to be a condition that the value of his swimming speed, that is V0, what we have taken over here, the magnitude of the relative velocity with respect to water, that should be greater than the flow velocity. If that is the case, then he can always achieve a situation where what is happening is his net velocity is along the perpendicular. So that way his path length will be minimum. So in this, we can say if the magnitude of the swimmer's velocity with respect to water is less than the magnitude of the water's velocity, or in this case, sorry, is greater than, not less than. The flow velocity is less than. So if this is happening, that is swimming speed is greater than the water's flow speed, then the minimum path length will become the width of the river itself, because the net velocity of the swimmer is along the y-axis, that is perpendicular to flow. Okay. For the condition that V0 sine theta balances VW, or theta is sine inverse of VW divided by V0. I'll show this with a numerical example also. So in this case, basically what we want, that the net velocity should be along this line. So if the net velocity is along this line, then he ends up reaching here. Even though his body is tilted like this, he ends up reaching here. So he crosses the river with minimum distance. Okay. So ultimately we get that minimum displacement is d if theta is equal to sine inverse of this. But the condition for this is that his own swimming speed should be greater than the water speed, because otherwise this equation will not make sense. Sine theta cannot be greater than 1. So for example, suppose the flow velocity of the water is 3 meters per second, and the swimmer's speed with respect to water, or V0, is 5 meters per second. Okay, and the width of the river is, let's say, 20 meters, or let's say 200 meters. Okay, then you can see that for this data, for minimum time, okay, he should take theta should be 0, and that minimum time will become d divided by V0. So 200 divided by 5, or 40 seconds. Okay, but for minimum distance or path length, the minimum path length here will become d, which will be 200 meters. Okay, and theta should be sine inverse of 3 by 5, or 37 degrees. So for this second case, he will have to swim at 37 degrees. And so I'll also show you the time taken will be more. He'll be compromising on time in order for his path length to be minimum. So he will have to swim in a direction which is making 37 degrees with this perpendicular. So that his net velocity going to be like this. So he ends up. So this is the minimum path case. Whereas for the minimum time case, he will swim with his velocity of 5 in this direction. The river will flow at 3. So his net velocity will actually become in this direction. And he will end up reaching here. So his body is oriented like this, but he will reach here at the minimum time. So the important thing also here is that in this particular case, for this case, you can see that his displacement will be this, okay, where this width is d. Now here you can see that because his net velocity in this case his net velocity will be 3 I cap plus 5 j cap. Okay, so his net displacement will be 3t I cap plus 5t j cap. Okay, where 5t is equal to d. Okay, so t is equal to that much. Okay, so this will be 3 into 40 whole square plus 5 into 40 whole square. So you'll see his net displacement is a lot more. Okay. So it's almost 230 something meters. Okay. He's compromising on distance.
Sir,
Yes.
what would be the case for minimum displacement when the velocity of the swimmer is equal to or less than the velocity of the river?
So see, when the velocity of the swimmer is equal to, or it can even be, for example, less. in that case, now the minimum path length thing is more complicated. It is not going to be d. It is greater than. It's going to be greater than d because he cannot cut the drift, and that's why that part is more critical. We have to solve it by calculus. There is no direct method to solve it. Like here we are doing by vector algebra. No?
Yeah.
Understanding the point? Okay.
So
So
wouldn't he just flow with the river?
ha. So it will be at some angle with respect to the river, and we have to calculate that minimum distance by using calculus. So I'll show that next to you how to do that. Okay.
Okay.
So there is one question like that in HCV also, where the person's swimming speed is less than the flow velocity of the river, and they've asked you to calculate that minimum path length. Okay. So it's towards the end of the kinematics exercise. So anyway, this value here, 40 into root 34, will be about 233 meters. So you can see here that the distance he is covering, he's compromising on that when the time is minimum. He's covering the, like he's clearing the river in the minimum time of 40 seconds, but he's having to cover more distance for that. Whereas in the second case, when the minimum distance he covers, that is 200 meters. But what about the time in this case? So for the time, we go back to that equation that the y component of displacement is y component of velocity into time, sorry, Vy into time. So d is going to be v naught cos theta into time. So in this case, theta is 37. Okay, so you can see the time taken will be d divided by v naught cos 37. So 200 meters, but divided by the swimming speed, which was 5 into cos 37, which is 4 by 5. So this will become 50 seconds. So in this case, the time he is taken is 50 seconds. So he's having to compromise on time. In order to achieve the minimum distance, he will actually end up swimming for a longer time. Whereas if he wants to keep the time the shortest, he will have to compromise on the distance he covers. He'll have to cover a distance of more than 200 meters or 233 point something. So again, this is something that you need to understand, that we cannot do both the things simultaneously. Either you keep the time shortest, but in that case, you will allow yourself to swim a longer distance. Your net displacement will have a longer magnitude compared to the other case. Or you want to keep the distance covered the minimum, but in that case, you will take more time to cross the river. Okay, and then we will come to the other case of this one where the flow velocity is too large for you to be able to swim perpendicularly. You will end up always having some amount of drift, but how to minimize that drift we will discuss. Okay, now let's come to a case where if the flow velocity of the water has a magnitude which is larger than the swimmer's velocity. Okay, or in this kind of case, we would write it like this, that then the minimum path length, that would be how much? Okay. Even this, in this case, however, the minimum time would be still d by v naught. And for that, theta should be 0. This still holds. Okay. But the minimum path length here, this cannot be d. Okay. Because you can see that the x component of displacement is equal to the x component of velocity into time, which is Vw minus Vo sine theta in that standard diagram into the time. Now this quantity here, this cannot be 0 for the condition that Vw is greater than V1. Okay, so therefore the x component of displacement cannot be 0. Therefore minimum displacement is greater than d here, cannot be equal to d. Okay, so that is the situation. So he cannot basically swim. There's no way he can cut the drift. He cannot swim in the direction which is perpendicular. I mean, he cannot have a net velocity along the perpendicular. No matter what direction he swims in, he will always have some kind of drift downstream. Even if he starts swimming upstream, he will still end up drifting downstream because the water's current or the river's current velocity is too much. He cannot overcome that with his swimming. So this is this kind of situation. Okay. Now we'll take a numerical example and solve this. So what we'll see is that whatever angle he swims at doesn't matter. Even if he swims at theta equal to 90 degrees, which is completely upstream, he will end up drifting. So he wants to minimize the drift. He has to sort of compromise and select a certain angle for which the displacement will be minimum. So let's see how to calculate that angle using maxima minima concept from calculus. So this will be his net velocity. And accordingly, this will be his net displacement. Okay, so while it is greater than d, but how to calculate? Now, how to find S minimum and the condition for it? Okay, so we use local maxima minima condition from calculus. Okay, so once again, so let's now take an example problem where this thing is, let us say now 4 meters per second, whereas the flow velocity of the water is now 5 meters per second. So you can see that flow velocity is greater than the swimming speed. So for a general theta, for the above case, for any theta, you can see that as a vector, this quantity is becoming 4 minus sine theta I cap plus cos theta j cap. Okay. And this is 5 I cap. So now the net velocity of the swimmer, which is the sum of these two. So the net velocity of the swimmer is becoming 5 minus 4 sine theta I cap. And as described above, this cannot have an x component which is 0. Now. So that is why he cannot cut the drift. The minimum distance will have to be more than the width of the river. Let's also take a case where the width of the river is also given to us. D is, let's say, 600 meters. So now we want to find the minimum, okay, distance traveled and all that. Okay. So now you can see from this that okay, where Vx will be greater than 0 for any theta. So now how do we calculate the minimum of the displacement? Okay. So now from here, the concept that we use is his net displacement is his net velocity into time. So and second equation is D is equal to Vy into T. So we have 600 meters is equal to Vy, which was 4 cos theta into T. This is our second equation. Okay. So these two equations now only will have to be analyzed in such a way that we are minimizing the magnitude of the displacement. So now in this example, okay, just make a note up to here, then we'll discuss how to set up. Okay. And if you've noted down, then from here only try and work it out that how we can now from equation 1 and 2, how we can express the total distance covered. Okay. And from that total distance covered, how we can find the condition for it to be minimum. How we can find the condition for total displacement's magnitude to be minimum. Okay, so now let's see how we will set up the condition for the displacement to be minimum. Okay, so now in this set of equations, what you can see once you've reached this point where you understood equation 1 and 2, now you can see that the magnitude of your net displacement, this is your path length, that is basically equal to what? It is square root of Sx square plus d square. So it is square root of Sx square plus d is a fixed quantity. We cannot change that. D is, so therefore, for mod s to be minimum, okay, Sx that must be minimum. But at the same time, we've already seen here that Sx cannot be 0. We already understood this thing, that because this velocity's x component is greater than 0 for any theta. So this also shows us that Sx is greater than 0 for all theta, for any value of theta. Okay. So we want to minimize it, but it can't be 0. So how to minimize it? So from equation 2 above, we can see the time can be written as 600 divided by v cos theta. Or if I write it parametrically, it is d divided by v naught cos theta, where v naught is the magnitude of the swimmer's relative velocity. So substitute this in equation 1. So we're getting x component of displacement as 5 minus 4 sine theta into 600 divided by 4 cos theta. So as you can see, we are getting it as a function of theta, or we can write it parametrically as Vw minus Vo sine theta multiplied with d divided by Vo cos theta. So further we can write the x component of displacement as, in this case, 5 by 4 sec theta minus tan theta, the whole thing multiplied by 600. Or we can write it as P by Vo by Vw sec theta minus tan theta, the whole thing multiplied by t. So this is where what we have done is we have got this thing as a function of theta. So for minima of Sx, what we do is, okay, second derivative should be positive at local. So this thing will give us the condition for minima. So now this becomes a calculus problem, as I told you earlier. So we have to solve it that way. So the question in HC Verma has different values, okay, but it has the same condition. I have taken the values that V of the water is 5 and the swimming speed is 4. HC and the width of the river is 600 meters. Okay, HC Verma question will have different values, but the method of solving is exactly the same. So we will complete the solution here, and later please complete that question also yourself. So with this, we cover all the various cases of relative velocity between a swimmer and flowing water. So any question related to this concept you can handle. Okay, so let's see how we will implement this maxima minima concept now. Okay. So you can see that this thing as a function of theta now is 5/4 sec theta minus tan theta, the whole thing into 600. So the derivative of that function is differentiation of this term. So that is now sec theta's derivative, you remember, is sec theta tan theta, and tan theta's derivative is sec square theta. So this is the derivative of that function. So derivative being 0 means that this term should be 0, which means that on factorizing this, be 0. So one is that sec theta is 0, which is not possible, okay, because sec theta is greater than equal to 1 or less than equal to -1 for all theta. The other possibility is that 5/4 tan theta minus sec theta is equal to 0, which is the same thing as 5/4 sin theta minus 1 into 1 by cos theta is equal to 0. So that basically means that this should be equal to 0, because again 1 by cos theta cannot be 0. So sin theta. So sin theta should be 4/5. So that means theta should be equal to 53 degrees. So this shows us that for f theta, which is basically Sx, to be minimum, theta should be equal to 53 degrees. So once we know that, then we know that this is becoming 600 into 5/4 sec 53 minus tan 53. Sec 53 is 1 by cos 53, so 5/3, and tan 53 is 4/3. So 25 minus 16, 9. 5 is 16. So the minimum value of Sx is going to be 450 meters. So the minimum value of the displacement is 750 meters. So the minimum path length with which he can cross the river is 750 meters. And for that, he has to swim at an angle of theta equal to 53 degrees with respect to the perpendicular line. So that becomes the complete solution for this. So I'm just minimizing this a little further now. For you to go through this. So this is obviously more of a JEE Advanced type of question because it's lengthy and it has an application of both vectors as well as calculus with maxima minima. Okay. But you should also remember this as a special case. at least you should remember the concept for the conceptual type of objective questions also. That if the swimmer's speed is small compared to the water's flow velocity, the water's flow velocity is too much, then he cannot have a situation where the net path in which he's swimming is perpendicular. He will always end up drifting. And if you want to calculate that minimum path length, then you have to go through this entire calculus process. Okay, so this is, as I was saying, one important type of application of relative motion. Now we will see the next type of application where we also have the concept of relative motion. Its application when we throw a projectile from a moving object. Okay, so those type of examples. Projectile launched from a moving frame. Okay. So you have seen a couple of questions like this in HC Verma also before, for example, but now we will look at more detailed examples. Okay. For example, we have a vehicle which is moving at a speed of 10 meters per second. Okay. And now from this vehicle, an object is launched. Okay. So a ball is thrown from the roof of a vehicle moving at a uniform speed v1 equal to 10 meters per second. Now this ball is launched at a speed at a velocity of magnitude u equal to 50 meters per second at theta equal to 53 degrees with respect to the vehicle. So find the time of flight, maximum height, okay, and range. Assume the ball falls back on the vehicle. So the range of the ball as seen in the ground frame or as seen relative to the vehicle's frame. So this is a situation at t equal to 0. Now the ball is going to go something like this. And we assume that when it lands, still lands on the vehicle because the vehicle is long enough. Wait a minute, I'll just make a correction to the diagram. I'll just have to make a correction to the diagram. The ball will have to be, actually, if we want this situation, the ball will have to be launched from the back of the vehicle. Yes. So let's assume it's a longish kind of truck or a railroad car or something like this. Okay. So this is moving at a speed of 10 meters per second. And at time t equal to 0, we have launched this ball, projected it like this from the back. Okay. So ball goes like this, and by the time the ball lands, so the vehicle is here. This is at some time t. So this is now the proper diagram.
Sir,
Yes.
so in the third question, we have to still assume that this ball is falling on the back of the vehicle.
In the third question, we have to assume that the ball is
Falling on the back of the vehicle. By the time.
not on the back of the vehicle. It will be falling somewhere on the front of the vehicle. No, beta? Because see what
Yes,
is
sir.
happening now with got it? No?
The third question is. Third question is written.
Yeah,
on
we
the
have to
black
assume
tire.
that the oh sorry, I'll change it from the back of the vehicle, but it falls. It falls back on the vehicle. That is what it means now. Okay, so it does not fall on the ground. Okay, it falls back on the vehicle's roof only. That's what the question means. Understood now?
Yes, sir.
Okay. So basically, when you're calculating the range, the y component of displacement should again be 0 because it's coming back to the same level, which is the level of the roof. Okay, so understand the important thing here that what is the projection velocity of the ball in the ground frame? Yes, very good. Time of flight is correct, Siddharth. Height is correct. Now the range you have calculated in which frame, beta? Have you calculated in ground frame or with respect to the vehicle's frame? That is the important thing, No, so in the vehicle's frame it will become different. In the ground frame it will become more. So what you have to understand that this projection velocity that we have given, u equal to 50 meters per second at theta equal to 53 degrees. This is the projection speed or the projection velocity relative to the vehicle. Okay. So it is like this, that in the vehicle's frame, the person standing here, he is seeing this like this. Okay. So this is the velocity of the projection velocity of the ball with respect to the vehicle. That is our 50 cos 53 I cap plus 3 sine 53 j cap. So that is becoming 40 I cap plus 30 j cap. Oh, sorry. It's becoming 30 I cap plus 40 j cap. Meters per second. Okay. This is the initial velocity of the ball with respect to the vehicle. But the vehicle's own velocity is 10 I cap. Okay. This V1 is equal to 10. Yes, very good. Now that's correct. Okay. So you can see from this and this now that with respect to the ground frame, what will happen is that the projection velocity of the ball in the ground frame will be this. So with respect to the ground frame, the projection velocity of the ball is 40 root 2, and theta with respect to the ground is 45 degrees. So you can see that ux is 40, uy is 40. So time of flight is 2 uy by g. So that is 8 seconds, provided I take g as 10 meters per second square. And maximum height is uy square by 2g. So that is 80 meters. Yeah, I'll come to the range with respect to the vehicle also, and the range is ux into time of flight, so 320 meters. Okay, so this is what this guy is seeing, that this guy is standing on the ground. What he is seeing, that t equal to 0, with respect to him the ball is being thrown at 40 root 2 meters per second at an angle of 45 degrees, and the ball goes like this. Lands here at capital T, which is 8 seconds. And in the process, the ball achieves a maximum height of 80 meters. And this total range with respect to ground frame, is 330 meters. Okay. Now we can see one more thing, that this point on the truck from which we had projected, suppose this point is A. Okay. So this point on the truck is now somewhere over here. And this point where it's landed, that is somewhere over here. So this is the range with respect to the truck. So we want to calculate this range. So we can do it like this also, that R prime is the range in the vehicle's frame. So in this diagram, you can see R prime will be equal to R minus displacement of the vehicle, where the displacement of the vehicle is this one. So this should be speed of the vehicle into time. So 10 into 8 seconds, 80 meters. So the range with respect to this is 320 minus 80, or 160 meters. This is one way of calculating the range. The other way is that we can actually look at the projectile motion in the frame of the truck only, and use projectile motion equations to find the range. Sorry, 240 meters, my mistake, 160. Yes, thanks for the correction.
Sir,
Yes.
sir, can you minimize the screen?
Yeah. Okay, so now we can also understand the projectile motion alternately as seen by an observer standing on the vehicle, okay, in the vehicle's frame. With respect to the vehicle's frame. So once we are standing on the vehicle, in our frame, the vehicle becomes stationary. Okay. But so with respect to the frame, the projectile was fired at a velocity of the ball with respect to the vehicle, which was 50 meters per second at an angle of 53 degrees. Okay. So the initial velocity of the ball with respect to the vehicle was 30 I cap plus 40 J cap in meters per second, that's given. Okay. Now you can also see that the acceleration of the ball in ground frame is acceleration due to gravity, and acceleration of the vehicle is 0. Okay, so this fact now tells us that the acceleration of the ball with respect to the vehicle is acceleration due to gravity only. Okay, so the equations of motion will be just as if it's a regular projectile. So the height, the time of flight, and this value of range, which we had earlier in our diagram labeled as r prime. So you'll see that h is equal to the y component square by 2g. Time of flight is 2uy by g. So all those formulae we'll use. But the values of v that we'll be using is this. Okay, so in the projectiles frame, this is what is happening. And the vehicles frame, this is minus 10 j cap in meters per second square. So you can see that in the vehicles frame, it's again 80 meters, there's again 8 seconds, but the range is now ux into time. So ux is 30 into 8 seconds, 240 meters. So there is another way of doing this calculation. Okay, now one last additional concept we will look at in relative motion as we wind up this chapter is a new type of physical parameter for us called the approach velocity. Or relative velocity of approach, which we denote with the symbol V approach like this, or alternately separation velocity or relative velocity of separation. Okay, both of these quantities being defined with respect to two moving bodies, with respect to two moving objects or particles, whatever. Let's understand this as an additional concept. And this concept is not only used for solving kinematics type of problems, but also used for solving certain types of constraint relations, the type you have seen in Newton's laws also. Yeah, sorry people, I just had some technical issue at my end, so the screen got frozen. Okay, so we will quickly discuss about this concept, and then we will maybe look at the applications in the next lecture. So the idea is that if the two particles, let's say A and B, are moving such that they are coming closer. Okay, so by that we mean that they are approaching each other, which also means that the distance between them is decreasing. Okay. Then they have something called an approach velocity. Then the V approach that is given by this relation that we'll show below here. So for example, suppose we have two particles which are right now located at a position like this. A is located here, B is located here. The distance between them is S. But what is happening is that A is moving with a velocity, let's say some random velocity like this. It could be in any direction. And B is moving similarly with random velocity like this, let's say, where this angle is, let's say, alpha, this angle is, let's say, beta. So this is the situation at t equal to t, let's say, at this instant. So what will happen is that after some time, A would have reached somewhere here, let's say. E would have reached here at some time t plus delta t. And in that much time, let's say B would have reached here at time t plus delta t. So you can see that at this new time, the distance between them has decreased. S minus delta S over here. So they are approaching each other as a result of that. So you can say now that at the instant t equal to t, when their instantaneous velocities at time t equal to t, when their instantaneous velocities are the vectors dA and dB as shown in the diagram. Okay, the approach velocity it will be given by a special term, which will be VA's component towards B plus VB's components towards E. And this approach velocity is equal to the instantaneous rate at which the distance between them is decreasing. So this is how we express the approach velocity in a general situation like this, where two objects are moving with some random velocities. Okay, they're not along a straight line or anything like that. So they are moving with some random velocities, but such that we can clearly see that the velocities are pointed in such a way that after some time the distance between them is decreased, or at that instant they are approaching each other because the distance between them is decreasing. Then the value of this approach velocity, which is minus ds by dt, will be given by the component of A's velocity directly towards B plus the component of B's velocity directly towards D. So that in this diagram you can say is VA cos alpha plus VB cos beta. Okay. So this is the new definition for us of the concept of approach velocity. So just note this down and we'll conclude today's session here. And we will look at some applications of this concept in the next lecture. And from there on, we will start with circular motion. Okay. Applications will just take a few minutes. We will discuss. So mostly in the next lecture, we are going to start with the circular motion part, which is the next chapter. So that's it for today's session, people. Wish you all the best and have a nice day.
Thank you, sir. Bye.
Sir, thank you.
Just a second, I'm muted.